Okay, I just spent a lot of time trying to get this all organized. I think I finally have the video sheet of it all organized, and as you can see by the clock here, it's 12:03. I've got a meeting to be at 12:30, but no worries. I'll return at 1 o'clock or at 1 o'clock to get this finished if we're not done by then. All right. So air pressure and moving objects. I wish we could do the calculation to look at some of the cool stuff that happens with Le Mans with Formula One racers. These are actually called wings, and they're reverse wings. And what they do is they keep the car on the road because of the air pressure, the Bernoulli effect, and the air pressure going over it. And then you look at the curveball on a baseball, and I really like the new slow motion cameras, so you can really see that spin on a baseball. For a long time, when the technology wasn't there, a lot of people, a lot of sports people even, and scientists thought curveballs was just an optical illusion. And no, it's real. It happens. And you want to see something really crazy, it's a knuckleball. But anyway, and we'll probably look at some of the physics of baseball in the next in the next lesson, which it's going to count as an exam score, just because I think it'll be more fun than doing an exam, and then I'll give you the final exam in the last week there of school. So anyway, and it'll be questions you've seen before, so you'll be fine. All right, so here we go. We get the Magnus force. This is called the Coanda effect, and Newton's third law is called the Magnus force. Okay, it'll deflect it. The spinning causes Magnus force, and so you get the spinning soccer ball, and it'll almost equal gravity. And so I've got in the Magnus force, the coefficient of drag on the Magnus force. So again, you got a coefficient of drag, air, density cubed. Now this is kind of interesting to me. You get the density cubed, then you get the number of spins per second, the frequency, and then times the velocity. And somehow we get a coefficient of we get a Newton out of that, but we do because you got density mass times volume. So that's a mass and the frequency times the velocity, yes, and so we wind up with meters per second squared. Sorry, I just said, so we got a mass times volume and just a number in front, and so we got density times volume, which is mass. These two things multiplied together actually do equal an acceleration. So you got mass times acceleration, just a number, so it is a force. That's cool. I just had figured that out myself right then. And so you get these crazy spins. All right, so go look at I've got like a little 5-minute video on Lionel Messi. I picked Messi because my son-in-law, stepson-in-law, my wife's oldest daughter, who's finishing up her PhD in sociology this next month, as a matter of fact, she's defending and graduating and all that. Her husband is from Argentina. And so there's 4-year-old son who's just a neat kid. Anyway, we were visiting and we were babysitting actually, and he's actually being kind of a little turd and crying and stuff for his mommy. And I was like, come on now, you're 4 years old. You need to get over this, all right? And so I showed him I said, and he loves soccer and he's proud of his Argentine heritage. And so I said, hey, you want to see the greatest soccer player in the world? Okay. He's from Argentina. Oh, okay. And then so we watched it, and I said, you know why he's the greatest soccer player in the world? He never cried for his mommy. So, and that seemed to work. Anyway, so you can watch those. So let's take a look at the actual homework some more. We'll go through this real quick. So we already did that one. We did that one earlier. Okay, now here's the Magnus force on which force makes a curveball curve? Well, we just talked about it. It's not drag so much, it's the Magnus force, which is created by the drag. Okay, because drag itself is not a force. Okay. And here's how we get a curveball to curve. And so what we're going to do is I slowly walk you through the formula here. Diameter. I used to have Billy Butler's head there, but I had to change it. All right, diameter. So you go through all that. Boom. All right. Now, foot is stationary. When you walk, your foot is stationary when it's pushing off. That means it is static. Okay. All right. Then look. Watch the Red Bull contraption. Okay. How high was he when he jumped out? It's a cool video. I highly encourage you to watch it. Um, now that Colonel Kittner, who jumped out at about a few kilometers less high, he didn't have all that fancy equipment. His glove was actually torn. He got frostbite, but he wasn't going to say anything. Those guys don't say anything. It's the right stuff, man. Because first of all, you want to be the one to do it. And if you say, "Oh, my glove's torn, I'm getting frostbite," you know what they're going to do? Scratch the mission, let someone else go. So, anyway, so if a bicyclist doubles, you know, and all of the variables, how much force must he apply to overcome? And it'll be 4 is your answer there. I'm pretty sure. I don't know. All right. So why does your voice get lower? We talked about that. If there's a planet that is okay, we talked about that. Franz Klammer, I want you to calculate his drag as he's going down the hill. All right. Oh man, why do I have my stupid Outlook on? There we go. And then you're going to compute how do you smoosh a beach ball under the water. That's going to be an amazing thing. That's going to be something else. All right. Okay. So in other words, my Newton force is only 1,500. So look at this. So you're going to find the buoyant force. This is how much force it takes to get a beach ball to stay underwater. It's an amazing amount of force. Okay. And so when you're doing that, we're going to calculate this. Here's what rho is equal to. You've done the volume. You did the volume of a baseball before. You've done that. And then G is 9.8 meters per second squared. So you're going to calculate this. You're going to use this. You're going to use this. Multiply those 3 together. And that's the amount of force you need to get that 2-foot diameter beach ball under the water. It's amazing. Let's save and submit. Let's see if that one question was right, because it didn't quite make sense. Oh, I'm late. So it won't give me the thing because that reminds me, I need to update the thing. All right. So out here,